All right, section 1.3 is called 12 basic functions. So hopefully you at least sort of remember from the past, especially from Algebra 2, that there's all these different families of functions. You haven't probably worked with that many of them, but the linear functions is like its own family. The quadratic functions, all the equations, all the functions that are graphed as parabolas, that's its own family of functions. And there's like always a parent function that's as plain as can be. So in the case of quadratic functions, you're just talking about y equals x squared, and then there's square root functions, and there's absolute. So there's all these different kinds of functions, and that's what we're going to be kind of building on that. Like, let's see what it says here. The preceding section has given us a vocabulary. Man, you're telling me, or you can say that again. A lot of different concepts covered especially in section 1.2, right? But the preceding section has given us a vocabulary for talking about functions and their properties. We have an entire book ahead of us to study these functions in depth. Like, that's the key thing as we head into this lesson, section 1.3. A lot of these new kinds of functions with their own new kind of graph. We're just going to be like showing it to you, but we're going to have to like wait for like a later chapter, sometimes like a much later chapter, to go really in depth into like why the graph is like that, or all that kind of stuff. But this is going to be like a challenging section in that way, but overall I would say like not very challenging. This is not going to have like that, like it's not going to hold that much weight for us here in Unit 1, because again, like in further, we're going to be studying these more in depth later on. But in this section, we want to set the scene by just looking at the graphs of 12 basic functions that are available on your graphing calculator. Okay, you can graph like anything basically on your graphing calculator. You will find, or almost anything, you will find that function attributes such as domain, range, continuity, asymptotes, extrema, increasingness, decreasingness, and end behavior are every bit as graphical as they are algebraic. Moreover, the visual cues are often much easier to spot than the algebraic ones. Duh. In future chapters, there we go again, just kind of giving context to this particular lesson. In future chapters, you will learn more about the algebraic properties that make these functions behave as they do. Like what's basically what's really going on with these functions, and what do they actually do with the input that you plug in, which obviously then leads to things like, why does the graph look like it does? Only then will you be able to prove what is visually apparent in these. Yeah, okay, here we go. So kind of running through these, I'm sure there's going to be some examples kind of sprinkled in along the way. Some of these you already know. This one is called the identity function, where it just pretty much ends up being y equals x. This is obviously a line with a slope of 1. Like this is basically, earlier, a couple minutes ago, I said the term like parent function. You could say that this is, probably the parent function of the whole family of linear functions. And I have this kind of, just this one time, I think, I want to emphasize that, these screenshots, I think from like the textbook, or a textbook, some textbook, the graphs look like just this, but like obviously lines go on forever in both directions. So I don't know, in my opinion, there should be like arrowheads kind of there. So feel free to add your own arrowheads kind of like here, for example. But the squaring function, I mentioned this already too in this video. I mean, this is a quadratic function where you have like an x squared involved. So this is a parabola, and again, this is like the parent function where it's just simply y equals x squared and not y equals 2x squared or y equals negative 3x squared plus 5x plus 7, you know. This is as basic as it gets, and that's the graph of it. The cubing function, I mean, to cube something. What does it mean to cube something? To raise it to the third power. So that's, I don't know if this is something you've ever seen before, but this is what the graph looks like for y equals x to the third power. And yeah, this is, you could call this the parent function for all cubic functions, but this is like the cubing function. And I mean, I guess I'll just say really quick that if you, like, even if you've never seen this graph before, you know what it means to raise a number to the third power. So investigating why the graph looks like this would not be very tough for you. The reciprocal function, do you remember what a reciprocal is? So, well, based on that, well, reciprocal, like for example, the reciprocal of 2 is 1 over 2. You know, and basically sometimes I call the reciprocal the refliprical. Get it? See what I did there? But anyway, to kind of, so the reciprocal function is that. And potentially a function you've never graphed before. And it just so happens that this graph, again, like, you know what it means to do 1 divided by an input, so you could analyze this numerically, which then leads to, you know, obviously look why this graph looks like how it does, and why there's these asymptotes. So there's a vertical asymptote here, and if you kind of investigated that, like for example, what's happening when you plug in 0.9 for x? What's happening when you plug in 0.5? What's happening when you plug in 0.1 or 0.01 or 0.0001 or 0.00000001? Like, what kind of output are you getting when you do that? And furthermore, can you actually plug in 0? No. So there is going to be no point that would be 0 comma something, and that's why, you know, we have like the graph behaving like this. Likewise, we have horizontal asymptotes because we can never have an output of 0. Like, we can get really close as we want, you know, as we plug in 6 for x, 7 for x, 700 for x, which is way off screen, 7,000, 7 million for x. Like, we're approaching 0, but we're never, ever, ever going to be able to actually output 0, which is why, you know, anyway, I've probably given some of these too much attention. The square root function, I would think there's a good chance you've seen this graph before, and how, like, you know, for this parent function in the whole family of, you know, we're taking the square root of an input. So that's what's going on there. And I mean, I don't know. Again, I gotta fight the urge to elaborate on all of these. So the exponential function, geez. Yeah, see, this might be the best example so far of what in the heck is going on here. And then look, hey, but this is the graph. So this says y equals e to the x. And again, it's like, it's hard for me to, you know, figure out or judge how in depth I should go. Like in unit 1 on this stuff that Like, we're going to learn way more about this officially in a later chapter. Like, I think chapter 3, if I, if you, off the top of my head, I think it's, unit or chapter 3 that we're going to be officially learning about this. For right now, yeah, probably a function you've never even heard of before. We'll learn about in a later chapter. And yes, I guess just to kind of make you feel a little better and not so uncomfortable about this brand new function you've probably never even like seen before. E, like this letter, this apparent, or it seems like that's a variable. It's not. E actually represents like a certain number. It's kind of like pi in that way. Okay, so E is basically about like 2.718, I believe. Kind of like how pi is about 3.14. So E is just some irrational number. So if that makes you feel any better, and then obviously we're still inputting, 1 for x, 2 for x, 3 for x, yada, yada, yada. I mean, again, in that same light, a function you've probably never even like heard of before, never seen before. We'll learn about this in a later chapter. Natural log of x. I'm not even going to try to go into this right now. It's just like way too early. But, I mean, for right now, I mean, you might have to just realize at least that there is a vertical asymptote on this graph at x equals 0. The sine function, I mean, maybe you've seen this, kind of function or concept before, like maybe in geometry or even algebra 2 at the way end, about like sine, cosine, tangent, and all these, trigonometry functions. But again, we're going to learn about this officially in chapter 4. So, I mean, but here's the graph, and the cosine function, same thing, just same thing. Here's what the graph looks like. The cosine function. And yeah, this, you could call this the parent cosine function, because it's not like there's a 2 out in front or a 3 right in front of the x, or like a -5 at the end here. It's just plain old y equals cosine of x. Okay, well, absolute value function, like this family you've definitely seen before in algebra 2, if not before that. It's y equals the absolute value of x, and it makes a v. And so you should at least kind of remember working with this family of functions. This one I think is last, right? Is this the last one? No. Is this the last one? Yeah. So the last couple here are, I mean, definitely new. Like, I don't know if you want to quote me on this or take my word, at 100%, face value or whatever. But this function probably does not hold as much weight as the other functions. Like, I guess what I'm saying is, if I were you preparing for the College Board AP exam, like, I guess I would make functions like this way less of a priority than learning about the other basic functions. The greatest integer function. So this is kind of how it's represented. And since I don't know how much we're going to follow up on this, like, ever again after this lesson and stuff, let's at least say out loud here what this function does. So notice how if you input 2 for x, the output is 2. Okay? If you input 2.5 for x, 2.5 right here on the x-axis, the output is 2. So if you input 2 point anything, 2.01, 2.9, 2.8754321, 2.67, the output is the greatest integer. Like it kind of defers back to the greatest integer. I mean, I can't say whole number. That would be, it's the greatest integer. Like that's the word. That's the thing. So, look up, and so the graph ends up looking like this. So look at here. Like, let's go to the negatives. So if you plug in -3, you're going to output -3. If you plug in -2.5, then the greatest integer, output is going to be -3. Interesting. Okay. So that's just kind of how it works. But again, I wouldn't lose sleep over, that function. The logistic function, geez, this makes me think of Calc BC, but certainly not in a scary way. But here you go. There's E again. So and is there also a horizontal asymptote right here? Like if we plug in, could we ever get something negative? No, I want to say, I mean, geez, I wouldn't bet my life on this right now. Just kind of putting me on the spot. But I think as x approaches negative infinity, so like if you plug in -5, this would be 1 over 1 plus e to the positive 5. It would be like -5. And so that's a positive number, but it's like really, really small. And then if you plug in -6, it'd be 1 over 1 plus e to the 6th, which is still positive, but even smaller, even closer to 0. So if you plug in -100, we're talking about 1 divided by 1 plus e to the 100 power. And remember, e is just some number. It's like 2.718. So yeah, I also want to say it's interesting that from the textbook, because I think there's also, maybe because that's literally the x-axis, and so like it's almost like the x-axis is the more prominent thing in the picture, and it's kind of like almost like hiding maybe. And I don't know. I don't even know what I'm saying right now. But there really should be a horizontal asymptote like on the x-axis, huh? So then some examples. I mean, 9 of the functions have domain. That's the set of all real numbers. Which 3 do not? So I mean, like, the graphs, even though for some of these are so new, just knowing what the graphs look like. I mean, what are the 3 of these where it's the domain is not everything? Like, yeah, everything, because this graph covers left to right. It covers everything. Like it covers, from negative infinity to the left to positive infinity to the right. So it's not that one. It's not that one. It's not this one. This one will keep going to the right forever and to the left forever. This is one of them. This is one of them because the domain literally does not include 0. Ooh, this is another one because, because of what's, taking the square root's all about, we cannot have any negatives in our domain. So there's another one. Not that one. This one. Is this the... yeah, this one. There's the third one. Yep, there we go. So that's kind of what these examples are going to be about. One of the functions has a domain, the set of all real numbers except 0. well, hopefully, and again, pause the video and try to, if you want to figure these out for yourself first, or try to. Question C, which two functions have no negative numbers in their domains? Of these two, which one is defined at 0? Which two functions have no negative numbers? Well, that one, like I already pointed out, and that one. Of these two, which one is actually defined at 0? Which one could we actually plug in 0 and be okay? Whether you just understand the equation already, like you know what this function is all about and what it does, because you know what a square root does. You might not understand what this one does, but at the very least you can look at the graphs and realize it's that one. Which one is defined at 0? That one. You could plug in 0. Next example. Only 2 of the 12 basic functions have points of discontinuity. Are these points in the domain of the function? So we have to identify first which 2. So which of the 2 graphs are not completely continuous, over the course of like x, from negative infinity to infinity for x? That one. And that one. Example 3. Only 3 of the 12 basic functions are bounded. Remember, if they just say bounded, it means it's bounded both above and below. Pause if you need to, because I'm probably going to be revealing these pretty quick here, so be quick to pause if you'd like to try these on your own first. Those are the 3 that are bounded both above and below, so we just say bounded. See, I told you for this one. This confirms it, that there is a horizontal asymptote at the bottom of this graph kind of thing. Example 4, be quick to pause if you want to try this on your own. 3 of the 12 basic functions are even. Remember what even means? Even means that it's symmetrical in regards to the y-axis. So those are the 3 graphs that are symmetrical to the y-axis, and therefore we can call them even. Example 5. Graph, okay, so this is not one of the 12 basic functions, but it is in one of the families. It's in the quadratic family, the squaring function family. So we're going to graph it, I guess, just on Desmos or your graphing calculator. So there's the vertex. 2 spaces to the right of the origin, shifted. On what interval do I go through? Yeah, I mean, more on this. Maybe next chapter, or I think next chapter, or later in this chapter. Shoot, I can't remember, but. We're going to be officially reviewing how to graph parabolas and stuff like that. So anyway, when it comes to, but here the assumption is that we're just going to Desmos or graphing technology to look at this graph and then go, oh, so where is on what interval is the function increasing? So 2 to infinity, x value wise. And yeah, there needs to be a bracket on 2. And then decreasing would be from negative infinity to 2 with a bracket. Is this odd, even, or neither? Remember, odd is symmetrical to the origin. There's symmetry with respect to the origin. Even means there's symmetry with respect to the y-axis. This one has neither. So does the function have any extrema? Remember, extrema means mins or maxes, relative or local mins or maxes, or, potentially an absolute min or an absolute max. And yeah, this has a relative minimum, which also happens to be an absolute minimum. So it's a minimum value of 0. Remember, the minimum or maximum values are y values, and then the x coordinate would be like kind of like a location of that min or max value. How does the graph relate to the graph of the parent function? I already kind of hinted at that at the beginning. Shifted 2 units to the right. Example 6. Does the graph of y equals the natural log of x? See, like, this example cannot expect me to go into like why it does or why it doesn't, because we don't know what this is. Like, we don't know what this function means, like what this function is doing to whatever input you plug in. So this example is basically, like, as far as this section goes, I guess it's just like maybe they expect you to know yes or no, and not even like why it's a yes or no, but the answer is no. More on this in chapter 3. So for right now, it's just like blind faith and just like, I don't know, mindless fact about this natural log or natural logarithm function that there is not. There's no horizontal asymptote, so this graph keeps rising forever. Like, very slowly, obviously, but it does keep going up and up and up and up and up forever. Makes you wonder, like, how far to the right do we have to go for the graph to get like as high as 100? Because there's 10 right there. So I mean, geez, to get to 100, what does the x value input have to be, man? Woo! And so that does it for section 1.3. Thank you for watching.